Okay, this is going to be a lesson on student learning task number 12, even and odd polynomial functions. To start off, I'd like you to get out a piece of clean paper, copy down the following graph, and identify the following properties. Make sure when you copy down the graph, you write down the ordered pairs and go ahead and note the properties listed on the left. Pause the video so you have time to do this. Okay, so as we look at this graph, we notice that it's clearly got a fourth degree because it has the same end behavior here and here. So on the right side, as x goes to infinity, the function goes to negative infinity. And also on the left, as x goes to negative infinity, the function also goes to negative infinity. In terms of intercepts, we see we've got a y-intercept. This appears to be at 0, but we're just going to have to go with it because we don't have any other better information. And we have x-intercepts. It appears there are 1, 2, 3, 4 of them at -3, -1, 0, and 2. This is definitely an even degree because it has the same end behavior, and it definitely has a negative leading coefficient. Sorry about the bad handwriting. It's increasing and decreasing intervals. Well, the first thing I'm going to do, oops, I covered up the point when I made it smaller. Oh, that didn't help. Undo that. Don't do that. Okay. So increasing, decreasing intervals. The first thing I'm going to do is I'm going to split my graph up into some sections. I've got one here. I've got one here. I've got one here. And I've got 1, 2, 3, 4 sections. The first section is an increasing interval. It's going to increase, so I'm going to make a list. I'm going to put my increasing over here. I'm going to put my decreasing over here. And I have an increasing interval when x is less than -2.22, because until we hit that maximum. We decrease from -2.25 until we hit this point at -0.5. So this is a decreasing interval. Then we increase again from 0.5 until 1.2. And then we increase again, or we decrease again after 1.2. So for maximums and minimums, we have two local maxes, or relative maxes. The first local max is, or it's actually an absolute max. The local max is 1.2. The absolute max, hold on. Hey, the absolute maximum is, oh, we are totally switching to the keyboard soon. The absolute maximum is 18. Oh wait, those are both 18, guys. I'm so sorry. I didn't realize those were the same the way it covered up that point. So we have, let's get this down here, we have an absolute maximum of 18, and then we have a local minimum of -3, because that's down here. So it's just a review of what we did yesterday on Friday, and I provided you with the graph. Again, if you need help working with your calculator, there is that video that you can check out that I posted on Remind to practice with your calculator. The answers to last night's homework are posted on Google Classroom. You can access them there. And I'd like everyone to please turn to page 17 in your packet. So what I want you to do is I want you to examine the set of functions I'm providing you with on page 17. These functions are all called even functions. Pause the video and take about 5 minutes and see if you can figure out the graphical relationship, the symbolic relationship, and the numeric relationship of these three functions. Okay, at this point you should have given yourself time to examine these and discuss. The first thing we're going to notice is the graphical. And we notice that all of these graphs are symmetric around the y-axis, otherwise known as the line x equals 0. Now, symbolically, I'm noticing that all the functions on page 17 are either even degree. This is like ridiculously big. Let's jump this down a little bit, shall we? There we go. Have an even degree or are absolute value functions. Now, numerically, when I look at the tables of all of these functions and I look at the numbers, like this is a great one, look at it right above here. I notice that all these numbers here have like a buddy number. They have a symmetric point. So when I look, for example, at -4, -25, or 208, it has a symmetric point for 208. When I look at -354, it has a symmetric point 354. So numerically, all ordered pairs XY have a symmetric point negative xy. I like to call that their buddy point, like xy has a buddy point negative xy if a function is even. So this is what it means graphically, symbolically, and numerically for a function to be even. Graphically means it's symmetric around the y-axis. Symbolically, all of these functions are even degree or absolute value functions. And numerically, when I look at their tables, all the xy points will have a symmetric point. I think I spelled symmetric wrong. Yes, I did. I forgot the R. Symmetric. There it goes. Point negative xy. So that leads me to a question. If I have functions that are even degrees, does that mean they are even functions? Are all even functions that are polynomials even degrees? I want you to pause the video, take about 2 minutes and discuss these two questions. Are all even degree functions even functions? Or I'm sorry, all even degree polynomials. Are all even degree polynomials even functions? Go ahead, pause the video and discuss these two questions for about 2 or 3 minutes. Okay, hopefully you've given yourself enough time to discuss them. So let's address this first question. Are all even degree polynomials even functions? And the answer to that is all even degree functions, and I've also kind of lumped absolute values in here. All even functions will either have an even degree or will be absolute value functions. But no, not all functions with an even degree or absolute values will become even functions. And the best way to think about this is our friend the parabola. Our friend the parabola is indeed an even degreed function. Let's grab one right here, shall we? Here we go, a beautiful parabola. Isn't it cute? It looks like it's even. It's symmetric around the y-axis. But if I take my parabola that I have reflected over the x-axis and given a horizontal or vertical transformation up, if I take, wait, hold on, I grouped the whole thing. Ungroup yourself. There it goes. If I take my parabola and I translate it to the right, it's still an even degree function. Is it an even function? No. Not all functions that have an even degree are actually even functions. So are all even functions that are polynomial even degrees? And the answer to that, of course, is no. Some absolute value functions are even functions. And again, this goes from the same thing with the parabola. As long as I only move it up and down and reflect it and dilate it vertically, but don't move it horizontally, it will still be an even function. So go ahead and flip to page 18, and here I've got a set of what are called odd functions. Pause the video and see if you can come up with the symbolic, the graphical, and the numeric meaning of what it means to be an odd function. Okay, hopefully you've given yourself enough time to look at these odd functions, and you'll notice that graphically all these odd functions have rotational symmetry around the origin. It's probably important to note that they have 180-degree rotational symmetry around the origin. Now, symbolically, all the functions on this page are either odd powered or odd degree polynomials or are cube roots. We have to remember, not all odd degree polynomials and cube roots are odd functions. Because again, we've got that whole horizontal transformation problem. The second we take an odd degree polynomial or a cube root and we translate it to the left or to the right, it's not going to have that rotational symmetry around the origin. The rotational symmetry will be around the symmetric point. Or sometimes we call that the starting point. So numerically, this is my favorite because you can always generate a table and figure out what's going on. This is like a gigantic font again. I don't know what's going on here. Numerically, all points x, y have a symmetric point, negative x, negative y. So for example, let's grab our little highlighter tool again. Here we've got the point negative 4 is 68, and here we've got the point positive 4 and negative 68. Over here we've got the point negative 210. Here we've got positive 2, negative 10. And of course they all contain the point 0, 0. You can see the same thing is true for these two as well. Okay, so what I'd like you to do is go back to where you wrote your warm-up and have a little challenge for you. I'd like you to sketch the graph of a polynomial function that matches all of the properties I'm listing here. Can you get them all to fit? Ooh, almost. Here, I'm going to zoom it out a little bit. Alright, so let's see. Go ahead, pause the video, and see if you can come up with, oh wait, I have to make a little note of something here. This notation you have not seen before. This notation is called interval notation. We use inequality notation. If you encounter this on a test or a quiz, I will always rewrite it for you. This interval right here is decreasing when x is less than negative 2 and x is greater than 1. And this one, and again, this is, I don't like this. This really even should be like this. And you can see I don't like this because it looks like an ordered pair. See, it doesn't look like the ordered pair. Negative 2, 1, and it's really negative 2 is less than x is less than 1. I hate that. Okay, now pause the video and go ahead and sketch this graph. Okay, so hopefully you've given yourself enough time to sketch the graph. I'm going to go ahead and put in what I know. I've got x-intercepts of -3, 0, 2, a y-intercept of 0, okay. I've got a relative minimum at -2, -6, so here's that point, and because it's a minimum, I'm going to kind of give it a little curvy. And then I got 1, 4, and I really feel like I should be like swoop. So let me just double check my end behavior. On the left it goes up, and on the right it goes down. This is not going to be that beautiful of a curve. But you get the idea. Oh, that's really ugly. Hell, hopefully yours looks better. And it is indeed only increasing between -2 and 1, and it is decreasing before -2 and after 1. I have another one for you. Go ahead and sketch the function that has these properties. Okay, so hopefully that gave you enough time to pause to work on these. So we've got x-intercepts. We've got end behavior that both go up. We've got a minimum. I'm going to just pretend that this is -15. So there's -3, -15, and there's 1, -15. Let's see how good of a curve we can draw. Not very good is your answer. Ooh, what is going on here? I feel like we should have some maximum. Do we? Oh, guys, I'm sorry. You should have a maximum of -1, 9. Just going to have to grab our handy dandy eraser. -1, 9. It's up here. And then it's just going to look like a really, really super ugly W. Meow. Alright, tonight's homework is on page 23 and 24. Explore more numbers 1 through 5. And I will turn the page so you can see the answers. Oh, too fast.